remaining stuff just includes exam 3, covering part 3, exam 4, covering part 4, and of course quizzes and assignments, part 4, covering part 4, shockingly enough. And they had a deadline on April 26th, end of the day, and then exam 5, the exciting final, covering all things, deadlines on Wednesday, finals week at 5 p.m. And as mentioned before, once you're done 4 exams, all the quizzes and assignments you wish to do, then you can look at your overall grade and see if exam 5 would make a difference. The way to do that is put in the best 3 exams, overall assignment grade, overall quiz grade, 100% hypothetically on exam 5 and the grade estimator, and compare that to your overall grade, the real overall grade. If it's a letter grade or more better, then taking the final could make a difference. As I mentioned before, anything you haven't done is already scored as a 0, so there won't be any like nightmarish scenario where on April 27th, suddenly all these zeros just suddenly appear on your final, etc. So your overall grade can never drop, it can only stay the same or get better. If you do see it like the overall grade drop, then let me know if something wrong has happened. And so your overall grade is your real-time grade in the class, and that can never drop, it can only stay the same or go up. Because anything you haven't done is treated as a 0. And so taking the final could help you possibly, but may not, but it can't hurt your grade. Before pressing on, also another thing people often ask me is they'll say, I'm still seeing my assignments and quizzes, why isn't dropping them? As I mentioned before, it doesn't erase them or delete them or put any mark on them, it just scores with your best 10. So if you check math, you'll see it's doing it right, even though no scores will vanish. If you do see scores vanishing, that's bad. Contact EIT because that's not supposed to happen. Okay, before heading to part 4, looking at deductive logic, anything about previous stuff, or stuff that needs more stuff. Okay. So part 4 takes us into the realm of deductive logic. And it is, we saw back in the ancient days, wartime, it's all about arguments. And as we also saw, when you get something, and you wonder, argument or not. And the way to tell is to ask those 2 classic questions, one of which is, what's the point? Not in the sense of asking like, why do this, or why should I care, but in the sense of what the person is trying to prove or establish. So there's a point, there could be an argument. So the second question to ask is, what is the evidence? What are the reasons, if any, being given? No reasons, no argument. No point, no argument. If you get a point and reasons, then you get an argument. So once you get an argument, the question is, what type? And so if the question is, what type, then the way to tell is this. Are the premises being offered to provide complete support or partial support? If it's partial, it goes back to induction, which we talked about in the previous section, which can be strong or weak. If the answer is it's trying to provide complete support, then the answer is deductive. As you saw, they can be valid, invalid, sound, or unsound. And so now we begin our adventures in deductive logic, looking at sort of the entry-level deductive logic, like categorical logic, and then moving to truth-functional logic, and then done. So what's our objective in Chapter 8? Well, we're looking at probably the oldest known logic. It goes back to our good dead friend Aristotle, who developed this, and then of course died, not because of the logic, but because of other reasons. And so we'll look at the following stuff. First, we'll be learning a new language. It looks like English, it's actually different. And in this language, there are only 4 sentences, 4 categorical claims. And the visual representation of these, at least in philosophy, we use what are called Venn diagrams, developed by the English mathematician John Venn, and now it's like a famous thing. In mathematics, they often use Euler diagrams, developed by a mathematician, this guy Euler, and they work the same way. For some reason, philosophers said, hey, we're going with Venn, and mathematicians seem to like Euler, but they both work basically the same way. Then we'll look at the notion of standard form, which is going from English to the categorical logic, which looks just like English but is slightly different. We'll also look at the dreaded square of opposition in various forms, and then look at the three rules, one of which we looked at before, conversion, which are used to make moves in this categorical logic. And of course, the end game is to decide whether a particular argument is valid or invalid. Now, as I mentioned, categorical logic is a language, and logic's a language, very explicitly so in the case of programming languages, which can be seen as logics, and they're presented as languages, things like HTML, C++, C++, JavaScript, Perl, etc. And the idea, of course, with a computer language is it has a logical structure to it, and it does stuff. It gives commands for a computer to run. And as you might imagine, all the programming languages evolved out of philosophical logic. And what we're looking at here, again, is sort of the most basic and oldest known logic, the categorical logic. Good question may be, why is it called categorical logic? Is it perhaps logic about cats? Well, it can be. It works fine with cats. But it's about categories. So it's about saying that things are in a class or not in a class. And there are only 4 sentences. So you can only say 4 general things in this language, but as we'll see, you can say a lot with just those 4 things. The first one, where x and y are just variables, would be all x's are y's. For example, all cats are mammals. The second one is no x's are y's. For example, no Republicans are Marxist. The next one is some x's are y's, such as some Democrats are socialists. And the last one, some x's are not y's, such as some Democrats are not socialists. Now, in terms of what the all, no, and some mean, it means this. All is easy. It means all of the things. No is also easy. It means none of the things. Some's a little trickier, though. In this version of logic, some means at least one. Possibly more, but at least one. And so we only really have, these quantifiers. All of them, none of them, at least one of them. And so that, oddly enough, covers pretty much everything, because if you talk about anything like the money, you either have all the money, no money, or some money. And so in a way it captures everything. Of course, as you might note, there's a huge range between some and all, or some and none. So that's why people developed more advanced logics later. So what do we use this stuff for, despite the fact that it's pretty basic? Well, one thing it's useful for is kind of entry into logic, because it looks a lot like normal English, and it's pretty intuitive the way it works. We all get all, no, and some, and so it's a good sort of entry into it. Also, again, it was a dominant logic for thousands of years, so it must have been kind of useful. It's useful for being more exact than sloppy English, with the all, no, and some, and so it does have some uses. And again, we now have more advanced logics that sort of supplanted it, but it's still something worth learning. So, again, our end game is to get to testing for validity. So, how do we get there? Well, kind of here's the process. So, we'll start off with sloppy English, and the idea is to extract from that, to translate into what's called standard form categorical claim. And then we'll be looking for arguments, and so the idea is to find the argument, and then test the argument to see if it's valid or invalid. So that's kind of the process. Messy English, get into standard form, test. So what's a categorical claim? Well, a categorical claim is any standard form categorical claim, or any claim that can be properly translated into a standard form categorical claim. of course, runs us in a circle, because they use categorical claim to define categorical claim. So how do we break the circle? Well, here's how we do it. True, standard form categorical claim is, a categorical claim is any standard form categorical claim, or they can be translated into it. And here's the definition of standard form categorical claim using a definition by example or ostensive definition. These are the standard form. So standard form categorical claim is any one of these. So if it's in this form, standard. If it can be translated into this form properly, categorical claim. Now the claims are made up of terms, and as you can see, each one's got two terms. There's a subject term, which is what the claim is about, and it's just like if you recall English, you get subject, predicate, language structure. The subject is what it's about. So if you say the cat is in the hat, subject, cat, or in French, gato. And it's in, Spanish. It's in the hat, which would be the predicate, and of course in French, un chapeau, which I learned from cat in the hat. And that's the extent of my foreign language skill. Yay, education. So that's the terms, the predicate and subject. Now logic, as you might suspect, is very finicky and picky. One reason is kind of a good one. The idea is you're supposed to be working in an exact system, so you want to be precise. You don't want to be sloppy. Another reason is also a practical one. What the logic has largely evolved into is, of course, computer programming, computer science, AI, etc. And currently, computers don't have much flexibility in terms of their programming. If you have a problem in the code, things go bad. It's not like a person who will, like a human who can stop and say, okay, I see what you meant there, so I'm gonna take care of that. If you write bad code for a computer, currently it's just gonna probably just stop or crash or get an error. And so one reason you have to be precise is, again, with current technology, directly programming it, they don't have that flexibility. Now, some AI systems do have that. You give them kind of a bad program, and they can sort of say, oh, kind of clean that up. But precision is still pretty important. Now, one of the picky things about categorical logic is this. In a way, it's kind of like Jeopardy. In Jeopardy, every answer must be in the form of a question. In categorical logic, in standard form, every term has got to be a noun or a noun phrase. Now, part of it, again, is just being picky, but part of it is for a practical reason. As we'll see in the future, we've got rules that let us do things to the sentences. And so, for example, if we take no fire trucks are purple, and we convert that, we would get no purple are fire trucks. And we can kind of figure out what someone means. But the reason why we use noun or noun phrases is because if we say no fire trucks are purple things, and if we convert it, we get no purple things are fire trucks. So it doesn't sound, dumb. So always nouns and noun phrases. Okay, so those are the initial basics. We have 4 sentences to work with, and these are the standard forms, and each sentence has got 2 terms: subject, what it's about; predicate, the quality it's got, and it's always going to be a noun or noun phrase. Before going to our next exciting slide, any of this stuff, or cats, that needs more stuff. Also, Cats are being made into a movie. There was a Broadway show for a long time, and soon it'll be a movie. I assume they'll do some categorical logic in Cats. Now, I mentioned the much feared Venn diagram. So a good question is, what are they, why are they, etc. Now, for each of our 4 claims, there's a lot of stuff going on. First thing going on is each one gets like a letter designation. Why? Well, part of it is just tradition. It's the way it was done, so that's the way we're doing it now. It's kind of like many things that we do. Like bad education. We just do it because we've always done it. Now, another reason to do it is a practical one, because it's slightly faster to say a claim than say all SRP claim. So it saves a little bit of time and maybe a little bit of pencil or ink or pixels in this case. And so you can refer to them more, in a briefer manner. So we get these 4 claims: A claim, E claim, O claim, I claim, which correspond to the 4 we looked at, nothing new here. And again, we call them that because it's slightly shorter than just sort of saying the whole thing out. To use an analogy, it's kind of like using someone's first name or nickname rather than using their whole name. It's often slightly faster. Now each of these claims has got a diagram. And there are other ways to diagram it. Like if you take another class, you might see an Euler diagram. But this is the standard Venn diagram, which consists of 2 circles. 1 circle for the subject, 1 circle for the predicate. And what the claims do is they say something about how the subject and predicate go together. Namely, how many of the subject are also the predicate. And again, the options are all of them, none of them, some of them are, and some of them are not. So what are these diagrammy things for? Well, they provide a visual representation of what the sentence is saying. They give us a visual graphic, an icon of what's going on there. Do we absolutely need them? Well, no. You can, understand them without the Venn diagrams, and as we'll see in the future, you can test for validity with Venn diagrams, but you can also test it without, just using this rules method. So they're not essential. Now, for our claims, again, we got 4, and they split into the following groups. One set is the affirmative claim. And affirmative claims are affirmative. They affirm stuff. They say something positive. The A claim, all S or P, and the I claim, some S or P, are both affirmative. They say something positive. The E claim, no S or P, and the O claim, some S or not P, they're negative. They are denying. There's also universal claims talking about everything, either all or none, and the A and E claim are universal. The O and I claim are particular because they're talking about some. Now getting back to the diagrams, here's how the diagrams work. Now right now, these 2 circle ones, we won't use these again directly because in a way, aside from showing us how these work, they don't do anything. And in the future, we'll see the 3 circle Venn diagram, which is the test for validity. So we're using these to get to this. And so again, these 2 circle ones, all they do is show us how each of the 4 claims work, but when we get to the actual test, we'll be doing 3 circles. But the 2 circle thing will kind of remain because we'll always be doing 2 circles at a time. We'll never do like all 3 circles at once. It'll always be 2 circles at a time. So again, these are visual representations of the claim. They show us with pictures what's going on. To use the obvious metaphor, think of your phone or laptop back in the old days, which you can return to. If you go to a command prompt in Windows or in Mac or Linux, you can see the old days of computing, which was all command line. So if you wanted to get to a new directory, you'd have to type in CD and then the directory. You want to run a program, you have to type which directory it is in and have run command. And you can relive those old days or experiencing them by going to your command line. And you'll find out pretty quickly that that's pretty annoying because you have to find where everything is to open programs, etc. It's obviously much easier to do what we do now, which is you look at your phone, you have a bunch of icons. And you look at your laptop, you get a bunch of icons. And these are like the icons, because visual images give us a lot more info. So what info is this giving us? Well, let's begin with the A claim, all S or P. So we have 2 circles, the S circle and the P circle. And each circle represents the zone, the category, the room, the bucket, whatever metaphor you like, the spotlight. You can use whatever metaphor you happen to like or hate the least. And so the S circle is the land of the S's. So all that is in that circle is S. And of course the P circle is the circle of P, and all that is in the circle is, of course, P. And then the center zone is where they come together, where they potentially mix. And so we're talking about in each claim, we're talking about the relation between these 2. Where do the S's go, where do the P's go? So the first one is all S or P. So this tells us that all the things that are S's, they're also in the P circle. And again, if you want to use the metaphor of a room, it's like these are two rooms, you know, kind of like in a hotel. You got like a, say like a bedroom area to like the living room area, and there's kind of like a mid zone between where you may think possibly bedroom, possibly living room, who knows for sure. And so this is kind of the middle zone. So if you say all S are P, what you do is this. You shade the circle where it's just S but not P to show there's nothing there. Now you can think of the shading metaphorically as anything you'd like. You can think of it as destroying that area, wiping it out. Or you can think of filling it in with concrete, so nothing's there. Or whatever metaphor you'd like. And so when you shade, this will seem perhaps kind of odd, you're saying nothing is there. Now I've seen on the interwebs the reverse, where shading is saying something is there. Now, interestingly or boringly enough, you could make that work. Because as long as you are consistent in how you shade, you could reverse it. Now as a practical matter, whenever you're taking a class, be sure to use whatever method is being used, because from the standpoint of someone teaching it, they can't tell whether you're a free spirit deciding to use your own method and getting it right, or you don't know what the hell you're doing, which they look the same, unless you realize, oh, okay, they're using the reverse method. But if it's during finals week and you're exhausted, grading hundreds of exams, you're not looking for free spirits, you're looking to get that stuff done. So as a practical matter, you could do it the other way, but it's always better just to go with the normal way for standard points. So when you do all S or P, we shade, 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 and so we're saying all S or P because there's nothing here anymore. So anything that's an S has to go here, because this zone is gone, filled with concrete, walled off, full of death rays, whatever metaphor you'd like. So that's what it looks like. All the S's are pushed here. Now the E claim is the negation. It says there are no S, R, P. So what we do in this case is we shade, because again, shading says there's nothing there. It's empty, it's destroyed, whatever metaphor you like. So here's the S's, here's the P's, and we shade in the middle, we're saying nothing there. It's gone. Big wall there. No one can get across. So this, all the S's are over here in their little S territory, if there are any. All the P's are over here in their P territory, and there's no mingling. It's all blocked off. So with no S or P, shade, shade, shade. Now, one bit of good news, or useful news, is this. Whenever you're shading all or no claims, these are the only ways to shade them. The A claim is always the kind of crescent or cookie with bite out of its shape, and the no claim is always the football shape. And when you go to the three circle diagram, we'll always shade that way. So we'll always do, you know, a cookie shape or a football shape. We'll never do like anything else. So you won't see, if it's done correctly, like a half a football or like a partial, you know, double bitten cookie. It'll always have to be those shapes. So if you're doing anything else with these, you know it's got to be wrong. It's got to be crescent or football. Now the O claim and I claim are a little trickier, because instead of doing obviously all or no, where we're shading, we're doing the X. So the X marks the spot, and it says again, some means at least one. So we say some S are not P, we're putting the X here because this is the land of S's, this is the land of P's, this is the land of things that are both. So we put an X here, you're saying there's at least one thing that is S, but is not P, because it's outside of that circle of P. And so you have the X there. Now with the I claim, you're saying some S are P. So it goes in the intersection. So here's the S, the P, here's the intersect, and you place an X there, you're saying there's at least one thing, and it's both of these. It's in the intersection. Now when you go to the three circle, that we'll see in the future, some claims become more of a problem, because with the A and E claims, the third circle doesn't matter, because you're always going to do, either for the all, the crescent shape, or for the no, the football shape. Now, for the O and the I, you'll always do an X, but as you can see, there's all kinds of places where the X can go. So as we'll see in the future, that can create potential problems. Okay, so at this point, what should you know? Well, again, we have the 4 claims. They're the only 4 claims there are in this logic. A claim, all S or P. E claim, no S or P. I claim, some S or P. O claim, some S or not P. These are universal. These are particular. These are positive. These are negative. And these are what the diagrams look like in terms of shading, X, and X. And these are the only ways to diagram it. So if anything else is going on, like you get like 3 X's and a couple areas shaded, something's going wrong. And in terms of what this is all for, as mentioned, right now it probably doesn't make like complete sense, but in the future, or if you've looked ahead, when you get to the 3 circles, we'll use these to test for validity. It's all about the circles. Before pressing on, anything about the circles, etc., that need any more stuff? So as previously mentioned, we're trying to go from everyday sloppy English, extract out the argument or arguments, and then get them into standard form. So this part is analogous to learning a foreign language. The idea being that you're going from what you already know and putting it into this new language. Now, fortunately, in the case of the categorical logic, even though it isn't English, technically speaking, it looks exactly like English. Not same words, same meaning, etc. And if you were doing this in French, it would look just like French, or Swahili, or whatever. Now, the objective is to go from normal, messy English to a standard form. And the standard form, as we saw, is one of those 4 claims. So it's got to be either all S or P, no S or P, some S or P, some S or not P, replacing the S and P with whatever it is you're talking about. So they'll all have the same structure. The way they'll differ is you'll have something different in the S and P slots. Now, here are some tricks for doing the translations. So our objective is to go from normal English, which can be kind of sloppy, to an all S or P, no S or P, some S or P, some S or not P claim. Fortunately, there are some ways to make this easier to do. Now, in some cases, we'll be able to do it pretty easily because there won't be anything weird or special about the claim, and it should be pretty evident how it translates. For example, if someone says every cat is a mammal, that's clearly all cats are mammals. Or if someone says no matter where you look in the Republican Party, you won't find any Marxists, that would be no Republicans are Marxists. Or if someone says, although Europeans once believed that swans were, well, a single color, it turns out that not all of them are white, there are some black swans. And that would be translated as some swans are black. Or it could be some swans are not white. And similarly for the other ones. And so in many cases, not that hard. You just got to ask yourself, is it affirmative or negative? Is it universal or particular? And of course, you can always guess because there's about a 25% chance you'll get it into the right type because there's only four sentences. So kind of the tricks would be to aim at which of the 4 does it belong in. So guessing gives you a 25% chance, and where does the subject and predicate go? And that gives you a 50-50 shot. So just guessing blindly, you have about a 12.5% chance of success. Not terrible. So what about things that are more complicated? Well, a word in English that messes things up often, making things more complicated, is the word only. Fortunately, we have ways of handling only. To make things even more complicated, the only differs from only. But again, fortunately, there are simple ways to handle this. The term only, if used correctly, always gives us the predicate of an A claim. And the way I always remember this is, and this won't be on a test or anything, I just remember with the memory device of OPA, which isn't, only predicate A claim. So for example, if someone says only sophomores are eligible candidates, well, someone may think if they're a sophomore, aha, they're eligible. So if they see a scholarship being being advertised and it says only sophomores are eligible for this scholarship. So I might think, hey, I'm a sophomore, I'm eligible. And weirdly, they would be wrong. Why? Well, because only sophomores are eligible doesn't mean that if you're a sophomore, you're eligible. It means that if you're eligible, you are a sophomore. So all the eligible candidates are sophomores, not all sophomores are eligible. Now, in many cases, of course, people just aren't careful. So if you see like a scholarship with this saying only sophomores are eligible, what they probably meant to say is only sophomores are the only people who are eligible are sophomores, or sophomores only, because people can be kind of messy with their language. But strictly speaking, that's the correct translation. Now, this can be useful on the side of evil if you want to trick people, because people are bad at only and not only. So if you want to be deceptive about things, that can be useful. Also, considering the path of evil, standardized tests, their whole point is to crush your dreams, to stand between you and your dream of law school, medical school, grad school, etc. And of course, they use all kinds of treachery. Well, not really treachery, but kind of. So they will use stuff like this because they know people will tend to get it wrong. But as long as you know this rule, you can avoid being defeated by only. Now, as I mentioned, to make matters worse, once you stick a the in front of only, that changes stuff, which is kind of annoying, but there you go. So the only, how does that work? Well, it gives us the subject of an A claim. And the way I remember that is TOSA, which sounds like something you'd get maybe a side of at Moe's or Taco Bell. Like, give me a dozen tacos with a side of TOSA. And just remember, the way I remember it is the only subject A claim. And again, this obviously won't be on the test or a quiz or anything. It's just how I keep it straight in my mind. Now again, the only can mess people up. So to give an example, if we say bats are the only true flying mammals, it may be tempting to say all bats are true flying mammals. But the correct translation would be all true flying mammals are bats. So annoying, but fortunately once you know the true rules, then it's easy to handle. And again, the way I remember this always is OPA, TOSA. Now what about time and space? Namely, whenever and wherever. Now these can be handled pretty easily too. Again, as long as you kind of know the tricks. And a lot of logic is just trickery. And as we'll see more of in the future, one piece of advice I always give about logic, sort of ironically, is to use a variation on Nike's slogan. Nike, of course, their slogan is buy our stuff, but more accurately, just do it. And I always add in, don't think, just do it. Which is a weird thing to say for logic, because you think logic is all about the thinking, but the idea is to be like a computer. The computer doesn't actually think, it just does. It just runs the code. And I found in all my years of teaching, the more people try to think their way through it, usually the worse it goes. So this will be the one occasion where I say the best way to do philosophy is don't really think about it, just do what you're supposed to do. And it works for logic, because as long as you just know what you have to do and you just do it without really thinking about it, so to speak, works out better. So whenever typically, since it's talking about all times or no times, it usually gives us an A claim, all, or E claim, none. So for example, if someone says, I always get nervous whenever I take logic exams, whenever would be all times. But then the question there is, so the part of it being an A claim is easy, then the question is, which is the subject, which is the predicate? So in this case, we'd look at it from the structure, but we can also kind of go with, you know, in this case, maybe thinking would help. So if we say, all times I get nervous are times I take logic exams, sounds kind of right, but when you think about it, it kind of falls apart. So it'd be like, if you say all times I get nervous are times I take logic exams, that would mean that every time you get nervous, you'd suddenly start taking logic tests. So it'd be a scenario where you always get logic tests with you, and like you're on a flight and it gets turbulent, you suddenly take a logic test and start doing them. Or, you know, you see the police turn on their lights and you're not sure if like you're speeding or not, you start taking your logic tests and start doing them. That would be possible, but weird. It'd be a weird sort of condition. The more reasonable one is this translation. All times I take logic exams are times I get nervous. Namely, if I'm taking a logic test, then I'm nervous. Wherever works the same way, except for places. So, for example, if it's he makes trouble wherever he goes, it would be all places he goes are places he makes trouble. So those are 4 translation tricks. In terms of how they'll show up on exams, assignments, quizzes, etc., would be, you know, you get something in normal English, and then there'd be, in the case of multiple choice, you know, like 4 options, one of which is, you know, correct. Or maybe a true false, like the correct translation of this is that. And it'd be obviously either true or false. Before pressing on, anything about this stuff that needs more stuff. Now we turn to another bit of pickiness for logic. Now, so far we've been looking at claims about all and no. So what if you're talking about an individual, like a particular person, like you say like Aristotle is a philosopher, or Tallahassee is a city in Florida, or Texas is a big state. How would you handle that? Well, it might be tempting to go with all, or some. In the case of some, you may think, well, some means at least one, so wouldn't we say like some? Because we're talking about a single person like Aristotle or a single city like Texas, that'd be like at least one. But then if you do that, it would be kind of weird. You'd say, for example, some Texas are big states, which is in a way kind of true, but not quite what we're saying. Or if we say some Aristotle are people that are logicians, kind of true, but kind of weird. So it's a slightly less weird, but still weird way of doing it. Well, the convention people have hit on for handling claims about single individuals, single person, single city, single whatever, is it becomes an A claim or E claim. But here's where you have to do a little weird kind of, you know, rigging. And here's how the rigging goes. You make the subject into a set, namely a set of all things identical to that thing, which will of course just be one thing. So all people identical to Aristotle would just be Aristotle, because the only person identical to Aristotle is Aristotle. So if we say Aristotle is a logician, instead of saying some Aristotle are logicians, we would say all people identical to Aristotle are logicians, because there's only one person that meets that condition, namely Aristotle. Or if we say that Tallahassee is in Florida, we would say all cities identical to Tallahassee are cities in Florida. Or if we say Texas is big, we would say all states identical to Texas are big states. And again, that's kind of you know, kind of messy, but it does work. And it's kind of a requirement if you're going to stick with the sets. Now, if you've had the math class that deals with sets and set theory, what we're doing is creating a set with one member. You know, all people identical to Aristotle is a set of one thing, namely Aristotle. So what about masked nouns? Well, masked nouns are things that if you combine them together, you just get more stuff, as opposed to, so if you take 2 apples and throw them in a bag, you've got 2 apples. If you pour water into a cup, you have more water. You have still one thing of water. Now the authors provide, again, kind of a picky way of doing it. So we would say, for example, gold is a heavy metal. We would say all examples of gold are heavy metal. Or you could actually kind of say, you know, all gold things are heavy metal things. So those are the kind of tricks of translation. Now again, the objective is to take the normal sloppy English and then get it into one of those 4 sentence types. And it has to be one of those 4 or it'd be not right. Before pressing on, anything about the tricks that needs more trickery? We now turn to the ancient square of opposition. And looking at it, you might say, that's not exactly a square, that's more of like an hourglass. And you would be right. So why do they call it the square of opposition? Well, back in the ancient days, it was a real square. Because back then it looked like this, because you had another relation. Now the authors, there's also, well, there's actually 3 versions of the square. So if you go on the Wikipedia, or see like another logic book, you'll see, if they do the history of it, you'll see multiple types of squares. Here's the original square, the one from way back. This is the square the authors use in the book. And there's also the 3rd square, which is the modern square of opposition, which is not a square at all, it's an X. So a very good question would be, so which square do we have to care about? Well, from the standpoint of the exams, assignments, quizzes, etc., this is a square for which one must care, because this is the one that shows up in the questions, etc. But it's good to know about the other squares, because when you go out and deal with other stuff, then you'll need to know not just the book square, but of course also the original square is worth knowing, and of course the modern square also worth knowing. And again, if you go take a logic class, depending on how it's taught, they may say this is the one you use. Now, does this mean that the others of them are wrong and that you're being deceived? Well, no. The reason why there's 3 squares is because of a battle between philosophers back in the early 20th century. And I'll show you how the square we need to know about works, and then go through the account of why we got 3. So here is the square of the book. And again, this is a square we'll use on the assignments, exams, and quizzes. It's the default square. So the square is a device used to more easily, hopefully, remember how the 4 sentence types relate. So it's basically a memory device. It's a tool for seeing how they connect. And the idea is that if you know the truth value of one claim, this can in some cases tell you or give you at least an insight into the truth value of the corresponding claims of the other types. So there's the A claim, E claim, I claim, and O claim. And what do I mean by corresponding claim? Well, here's how corresponding claims work. A corresponding claim in this context means that you keep the same subject and predicate, but you put it into the structure of the particular sentence type. So to give a concrete illustration, suppose we're going with the claim, all cats are mammals, our A claim. Now the corresponding E claim, that's to say, the E claim with the same subject and predicate would just be an E claim with cats as a subject, mammals as a predicate. So the claim, all cats are mammals, would be our A claim. The corresponding E claim would be no cats are mammals. Then of course, the corresponding O claim would be some cats are not mammals, and the corresponding I claim would be some cats are mammals. So corresponding claim is just kind of a concise way of saying you take the same subject and predicate and put it into that form of that claim. Now if we had a E claim, like no Republicans are Marxists, the corresponding A claim would be all Republicans are Marxists, the corresponding O claim would be some Republicans are Marxists, and the corresponding I claim would be some Republicans are not Marxists. And so by corresponding claim, that's what we mean. And so the idea would be if you know the truth value of one claim, you can get an insight or maybe even know the truth value of the corresponding claim of the other types. So what we do to use the square is we would know the truth value of a particular claim, like an A, E, I, or O, and then we'd use the table to see what this tells us about the corresponding other claims. So here are the relationships that exist in the author's square. First, there are contraries. That's between A and E. Two claims are contrary means, or inconsistent, means they both can't be true. But it does mean they could both be false. So, for example, if we say all Democrats are Marxist, that's contrary to no Democrats are Marxist. They can't both be true. Because if they're all Marxist, then it can't be true that none of them are. And if none of them are Marxist, then it can't be true that all of them are. But they both could be false. There may be some Democrats who are Marxist, and so the claim all of them are would be false, and the claim none of them are would also be false. Moving down, the next relation is contradictory. They're the opposite. If one's true, the other is false. If one's false, the other is true. So this holds between A and O and E and I. So if it were true that all Democrats are socialists, the claim, oh, some Democrats are not socialists, one of them's got to be false, and one of them's got to be true. In the E and I claims, same deal. You've got, if you have no Democrats or socialists, then the corresponding I claim would be that some are, and so they would contradict each other. So what you do to work the table is just go back to our types, the A, E, I, and O, and then swap out the subject and predicate for each one, and then you get your results. So, no Republicans are Marxist contradicts some Democrats are, or some Republicans are Marxist. One of them's going to be true, one of them's going to be false. So how will this show up on exams or quizzes or assignments? Well, typically it would be something like I would say, suppose it's true that no Republicans are Marxists, then it must be false that some Republicans are Marxists. That would be true. Our final relationship are the subcontraries, because it's below the contraries. Holds between I and O claims. Whereas the contraries both can't be true, but both can be false, some contraries can both be true, but they can't both be false. So if one is true, the other could be true, could be false. If one is false, the other must be true. So if we have some Democrats are socialists, if we know that's true, the O claim some Democrats are not socialists could be true, could be false. Likewise, if we know that it's false that some Democrats are not socialists, we know that's false, then the I claim some Democrats are socialists is going to be true. So with these, you can know some things about the corresponding claims. So that's our standard for the book, the standard truth table. Now, back in the original table, there was another relation. There was a fourth relation called subimplication. And subimplication is that you can go from an A claim to an I claim. So if A claim is true, the corresponding I claim is true. If you go for an E claim, the corresponding O claim is true. For example, if all cats are mammals, on Aristotle's logic, that meant that it was true that some cats are mammals. Now the reverse doesn't hold. If all Democrats are Marxists is true, it's true that some Democrats are Marxists. But if it were true that some Democrats are Marxists, it doesn't follow the all. Likewise for the no claim. If no Republicans are Marxists is true, it follows that it's true that some of them are not. But if some of them are not, it doesn't, not Marxist, it doesn't follow that none of them are. So it's a one way. Now the author's version, even though we leave out subimplication, kind of does give us the same effect. Because if this is true, then by this, it contradicts this, so this is going to be false, so this is going to be true. So you do get a subimplication indirectly, and likewise there. So you do end up having an original square. Now, why did they get rid of subimplication? Well, as I mentioned, it was thanks to, in the early 20th century, people like Bertrand Russell, famous philosopher, now dead, Strawson, famous philosopher, now dead. They got in a debate about what we'll see in the future, namely the conditional. So the question was, when you talk about all or no, does that have what's called existential import? Does it mean that you're talking about something? And here's how the debate kind of went. One side, well, you can use sort of a scenario. Suppose you go to somebody's house, and they say, shh, please be quiet, all my children are sleeping. And so, you're really careful and quiet the whole time. And then, like, just as you're leaving, you say, oh, what are your children's names, by the way? And the person says, I don't have any children. That would be weird. You might think you're in, like, some kind of horror movie. But, of course, what people said, or what one side said is, if you say something like, all my children are asleep, you only say that if you have children. If you don't have children, you don't say that. Or if I say something like, all my Maseratis are fast, you'd be perfectly reasonable to say, well, what type do you have? And if I say, I got none, that would be weird. So the idea being that if you're talking about like all, you're implying some. And likewise for none. If I'm talking about none, that means there's none of those things. Now, the opposing view was that you can say things essentially about all, even when you don't have any. Namely, this came out of the conditionals. So, for example, think of claims, to use some sort of silly claims from fantasy. If someone says all unicorns have horns, we would think that's true, because in mythology, if something's a unicorn, it's got to have a horn. There are no unicorns that don't have horns, unless they've been stolen by Tim Curry. So we would say, yeah, all unicorns have horns. We'd all agree to that. But we wouldn't say, okay, let's show me some unicorns, because we get that although all unicorns have horns, there are no unicorns. And so kind of the debate had sensible positions on both sides. Namely, again, if you tell someone, shh, be quiet, all my children are asleep, and they tell you, I don't have any children, that would be insane. But when you talk about things like, all vampires, are undead, yeah, that's mythology. But of course we have none of those things. So I think we can talk meaningfully about things that don't exist without committing to their existence. But then again, if we go around saying things like all my children are asleep and we have no children, that would be insane. And so the battle was, is there really that implication? So how do the authors get around that particular problem? And this is why the modern square has only got contradiction. Because if you have an A claim being true, namely, like all cats are mammals, the O claim, some cats are not mammals, has got to be false. Likewise for E and I claims. And then on the modern square, A being true tells you nothing about I or E on the modern square. So the author's version is kind of a compromise. The idea being that this works as long as you make one critical assumption. Namely, when you're talking about stuff, you're not talking about empty classes. So the A claim, when you make an all claim, there's something in the set. And in our normal common sense, everyday non-insane talking, that's true most of the time. So again, if someone says, all my marathons have been really good, and you say, oh, what's your fastest time? They say, oh, I've never run a marathon. You'd say, why? Oh, you're really annoying. We expect people to say in those cases that they actually have done something, that they've done marathon. Or if you go to a party and they say all the beer is in the fridge, and you open the fridge and it's empty, and they say, yeah, all the beer is in the fridge, but I have no beer, that would be a pretty short and annoying party. So in normal usage, we do mean, when we say all, we're also implying we're talking about something. Now, but then again, to be fair, we sometimes talk about all when we leave it open that whether there's something there or not. When we say all vampires are undead, or all unicorns have horns, etc. Or talking about Harry Potter. It's not true because there's no Harry Potter, but we can talk meaningfully about it. So as a practical matter, we go with this square when we're talking about normal stuff. If we're going to be strict, and hold it to the thing about the possibility of empty sets, then we have to go to the modern one. And so that is the long tail of why we have three squares. It's the battle of when you say things like all the beer is in the fridge, do you actually have to have beer? Are you implying there's beer? And normal people would say, you are, because that would be weird. So from a purely practical standpoint, for the tests, quizzes, and assignments, this is a square to use, but again, I would be remiss not to point out that there are three versions of the square, so if you take a logic class, you may see all three, or they might just, many current logic books just use this one, and that's the square that's in use. Okay, so before pressing on, any other square needs any more stuff. Okay. So recap, what do you need to know for exams, quizzes, and tests? Well, this square. No contrary, they both can't be true, holes between A and E, contradictories, they're never the same value. If one is true, the other is false. If one is false, the other is true. Holes between E and I, and A and O. And there are subcontraries, they both can't be false. Holes between I and O. So if one is false, the other is going to be true, and vice versa. Common questions would be, again, giving you a claim like all cats are mammals, and then saying if it's true that all cats are mammals, then which of the following is true? And then giving options, one of which is true. Okay, moving along. In addition to the square of opposition, we also have three categorical operations. So the square is used in terms of its function. Again, it's so we can reason if we know one particular thing is true or false. It tells us, or can tell us, about the other corresponding claims. So what do the categorical operations do? Well, to use an analogy, they're rules of moving the pieces around. Just like in, I like to use an analogy to chess. Each particular piece in chess has rules that governs how it moves. Does it move diagonally? Can it move one square? Can it move three squares? Or like in any sport, like baseball, there's sets of rules of what you can and cannot do. And in logic, the world's boringest game, there are also rules for how you can move the pieces. Now, so for each rule, and there's only 3, so we've got 4 sentence types, and we've got 3 rules for dealing with them. Each rule is the following stuff. One is how to make the move. Again, using an analogy to a game, it's like in chess or League of Legends or Axis and Allies, whatever game you might like. It's how the pieces can move. And of course, if you've ever played any game, not all pieces move the same way. I mean, chess is a good example where not all pieces move the same way. Or like in soccer, if you're the goalie, you can touch the ball with your hands. If you're not, you can't. And of course, also in baseball, there are different things you can do. Like if you're the pitcher, you can throw the ball, but you can't have like the first baseman pitching from first base. It's just not done. So there's the correct application of the rule. Now, what does correct application mean? Well, in this context, correct application means that if you apply the rule, your original claim and the claim you've changed with the rule, they mean the same thing. Being more formally, they are true functionally the same. That if the original is true, then applying the rule, the new claim is also true. Or if the original is false, the new claim is also false. But more informally, they still say the same thing, just in a different way. So, our first rule is our old friend conversion. Here's how the rule works. So again, for each rule, first thing to know is, what does it do? And the answer of a conversion is, you take the subject, the predicate, and they switch places. So a good question B is, when would you use this? Well, basically you'd use it based on what it does. Just like in baseball or any other sport, you use a rule when that situation comes up. So in this case, you'd use this when you need to switch your subject and predicate. When might you need to do that? Well, the answer would be in the following cases. As we saw, all 4 of the claims have to always have the subject first. So the subject term's got to be first. So if your subject is not first, then this is when you use the rule. When you've got to get the, if the predicate's first and the subject is second, you got to get them switched around in the right order. And so that's what it does. It says, hi there, I'm conversion. You need to get this flipped around. That's what I do. Now, conversion flips both ways. So you can switch subject and predicate, swap, and also swap the other way. As you might imagine, the way you typically be using it is, instead of swapping the predicate in for the subject, you'd be doing the reverse, swapping it so you get the S first and the P second. So when does it apply correctly? So the first thing is, what does it do? And the answer is, flips the subject and predicate. And the answer is, when correct. And the answer is, in the following cases. The ones that are in red are where it's the rule would be wrong to use. Why? Because if you apply the rule in those cases, they don't mean the same things. So first, the A claim. If we convert all S or P, we get all P or S. Why doesn't that work? Well, consider the following example. It's true that all cats are mammals, but if we convert that, we get all mammals are cats, which is not true, because it is true that all cats are mammals, but it's not true that all mammals are cats, because we're not cats, dogs aren't cats, possums aren't cats, sheep aren't cats, cows aren't cats, etc. So, not correctly applied there. The E claim, no S or P, if we convert that, we get no P or S. And that does work. Why? Well, to illustrate, if we say no Republicans are Marxist, then it follows that no Marxists are Republicans. Now we can see which ones work and which ones don't by looking at their Venn diagrams. So with an A claim, it looks like this, and if we flip it, it looks like this. And as you can see, they're not the same. With an E claim, looks like this, and if we flip it, it looks like that. So it looks the same. So with the I claim, some S or P, as you might imagine, since we know diagrams like this, and you flip it, and it looks the same, it works correctly. For example, if we say some Democrats are socialist, and we say some socialists are Democrats, that works. If one is true, the other is true, so okay. Lastly, for the O claim, some S are not P. If we flip that, we get some P are not S. So it looks like this. And if we flip it, we get that. And they don't look the same. So if we have some Democrats are not socialists, and we try to flip that to some socialists are not Democrats, they're not, one could be true, the other false. So E and I claims work, to say they're equivalent, and A and O claims are not. So how would this show up on quizzes, tests, etc., and how to use it? Again, the objective is you have something not in standard form. So, for example, if we have the claim no P or S, like no Marxists are Republicans, but Republicans is our subject, that is close to standard form, but not. Because standard form has to be no S or P. We would have to have it as no Republicans are Marxists. And so we'd use the conversion to flip that around. And so you use it when you've got to flip the subject and predicate, and so it would be cases where you have this or this, and that's when you would use it. And then it works correctly there. Now in these cases, it doesn't work. I mean, if you apply it, then you don't get the equivalent thing. And we saw back in the induction section that when you flip things inductively, it's the illicit inductive conversion doesn't work. But in this case it does because, well, obviously for the no, that always works. But the sum works when you mean at least one. But as we saw, if you're using the inductive reasoning, we were talking about statistical syllogisms, if you say a few few cats or lions, so few lions or cats, that doesn't work. But if we say some cats are lions and some lions are cats, true, because at least one cat is a lion, at least one lion is a cat, so okay. So how does this show up on the exams, quizzes, etc.? Well, a typical thing will be like a definition question, like true or false, conversion is, and just give the definition. Second common way is to say something like true or false is all S or P equivalent to all P or S. Now one of the assignments, actually kind of two of the assignments, is you'll have to do the following. One thing it'll do is it'll give you a sentence and it'll ask you to apply a rule. And then, so the first step would be apply the rule and pick which answer corresponds to that rule. So when we go over the other rules, we'll see this in more detail, but you'll have to pick, what would be, say, the conversion of something. So if I say, for example, some Democrats are not socialists, what is a conversion? And of course the correct answer would be some socialists are not Democrats. Then the next question would be, are they equivalent? And the way you tell is, again, by this information. In this case, the rule doesn't apply to the O claim, so it would not be equivalent. And so that's how you do that assignment. You take the rule, apply it, and you'll see, find the correct answer in the set. And then the next question would be, are they equivalent or not? And the way you tell is, you find out what the original is, and then if the rule applies correctly to the original, they're equivalent. If the rule does not, non-equivalent. So that's conversion. In the future, on Thursday, we'll move on to our next two rules, and then to more stuff. Before ending, anything about the stuff, to be or stuff that has been, that needs more stuff.